Hey, this is a continuation of the written response question review of the August 2015 chemistry Regents exam. And we are up to questions 73, 74, and I'm hoping 75, 76, maybe up to 78 in this video. See how fast we can do this. Okay, starting from here, pick a color, I'll go with green again. Okay, so reading for 73 and 74. Coal is a fuel consisting primarily of carbon. In an open system, meaning not sealed, closed, the carbon that burns completely in air produces carbon dioxide and heat. This reaction is represented by the balanced chemical equation below. So we have solid carbon, elemental, plus elemental O2 oxygen gas, yields carbon dioxide gas and some heat energy. Okay, 73 says, in your answer booklet, use the key to draw at least 5 particles in the box to represent the phase of the product. So a quick review. The arrow is called the yield sign, which means to give way to something, yield, or give up. The left side of the equation are the reactants, and you have your yield sign. And the right side of the equation are what you get, which are the products, because they were produced. Okay, so when somebody says the phase of the product, there's only one product, which is a chemical substance, which is carbon dioxide, and we see that it's a gas. So if I close this, let's see, and we go to the answer booklet, let's see what they gave us. All right, so this is 73 in the answer booklet. Delete those. 73, they gave us, oh, look at that, a box. And they want us to draw that carbon dioxide molecule. Okay. And they said draw at least 5. All right, well, sure. Here you go. We're going to draw 5 carbon dioxide molecules to represent the phase of a gas. So let's think about this. A gas. The particles should be not sticking together and should be separated by a bit of distance, quite a bit of distance, and they shouldn't be sitting at the bottom of the container. Gases fill a container. So let's try to do this. So let's draw at least 5 of these. So here we go. Oxygen, carbon, oxygen. That's one carbon dioxide molecule. Draw another one. Oxygen, carbon, oxygen. Oops, it's 2. Keep going. Carbon, oxygen, oxygen. It's 3. So it looks like planet Saturn to me. Another carbon dioxide molecule. And another one here. Sure, why not? I mean, there you go. They're filling up the entire container and they're separated from each other. That represents a gas phase. Done. Okay, so back to the test. So we can do the next question. Oop, no. Sorry. Okay. 74. On the potential energy diagram in your answer booklet, draw a double-headed arrow like that to indicate the interval that represents the heat of reaction. Okay, so quick recap on potential energy diagrams. Let's see how fast I can do this. Okay, so potential energy diagram. So we have a y-axis, x-axis. Okay, so the y-axis will be potential energy measured in joules. And the x-axis can be, they call it reaction coordinate, which basically means time goes on. Okay, so if we see, let's say, a graph or a potential energy chart or diagram that looks like this, let's start labeling this. So we have the energy of the reactants there. This is the amount of potential energy that the products have. So if you notice, the reactants have more potential energy than the products. We'd even call it, like, let's see, 0, 1, 2, 3, 4, 5. Okay, so you could see, let's say the reactants had 5 joules, the products have about a half of a joule. Okay, we'll get to that in a second. So the reactants have this much energy, the products have this much energy. Okay, now you're probably noticing this hill here, and that distance from the amount of potential energy that the reactants have up until the top of the hill, that is not the answer for this question because they asked for the heat of reaction, but you do need to know this gap here to the top of the hill. That is the activation energy, which is basically the kick in the behind that you need to give a reaction to get it started. You've probably noticed in real life, to get a reaction started, like to light a gas on fire, you need to give it a spark. To get paper to start burning with oxygen, you need to heat it up enough in the first place. You need to get some friction. So every reaction needs a little bit of a kickstart. So that is the activation energy. That is the kickstart. Now, if we try to do a little bit of math here, let's say we actually do the math and go, okay, the energy of the products minus the energy of the reactants, which looks like it'll be about, well, the products look like they're about 0.5 joules, and the reactants look like they're at about, according to our chart, about 5 joules. So if we do the products, 0.5, minus the reactants, 5, we get a negative number, negative 4.5 joules. If you notice the negative, that means that heat is being lost, which means that this is an exothermic reaction. So anytime you notice that the products have less energy than the reactants, well, how did the products lose energy? Well, the reaction must have given out some heat. So if you notice that the products have less energy than the reactants, that is an exothermic reaction. Okay, now to actually answer the Regents question. They asked to draw the heat of reaction. Well, do you see our calculation here? The energy of the products minus the energy of the reactants. That is known as the delta H, which means the change in heat or the heat of reaction. So products minus reactants energy, that is the heat of reaction. So if we basically took this and this, that gap, that is the heat of reaction. So if we go to the booklet, so let's go back to the answer booklet. Okay. And we go to the chart they gave us. Yep, see? Reactants, products. So let's label this. Okay, so we have our reactant, we have our products. If we notice, reactants have more energy than products. So this is an exothermic reaction. But what they asked us to do is draw arrows to show the region that is heat of reaction. That would be from the potential energy of the reactants to the products. So this area here is the heat of reaction. That's the answer. If they had asked us to label the activation energy, that would be up to here from the reactants. So this would be the activation energy, but that is not what they asked us for. So on a test, we would not want to put that. But just showing you, this is the spot that we want to label with the double-headed arrow. That's the heat of reaction. And there we go.